Hi, this is my conversation with Eric Jang. He's a research scientist on the robotics team at Google. His research ranges from sim to real to scaling end-to-end learning for robotic manipulation and much more. He also has a great blog that I really recommend you to read. I link it below. In fact, much of this conversation is about his last blog post called Just Ask For Generalization. I'm sorry if the video is low quality, but I have messed up the recordings. I'll do my best in the next episodes. But for now, enjoy my conversation with Eric.
Okay, Eric, so thanks for accepting the conversation. I really appreciate it. So to kick off the conversation, can you give us your background and what brought you into machine learning and robotics?
Sure, yeah. Thanks, Andrea, for having me on your podcast. Honored to be here. So I'm currently a research scientist at Google Brain studying end-to-end robotic mobile manipulation. The basic idea is that the last decade of machine learning has seen the subsumption of a lot of classical pipeline-based approaches for building complex algorithms into one big neural network. So in Vision, you had like the transformation from a multi-stage perception pipeline to a single neural network that does everything. And then similarly for many NLP tasks, same thing, audio, same thing. And then so a very natural question to ask is whether this will also happen for robots and what it takes to do the same thing for robotics. So for the last few years, I've been working on trying to put all of the capabilities of robots and the whole robotic stack into a single neural network. How I got into machine learning. So I've always been interested in robots. I think like my favorite movie growing up was The Iron Giant when I was like a very little kid. And I think in high school, I was doing like science fair competitions, and that got me thinking a lot about like what are the big questions in science. And naturally, one of the biggest frontiers is like understanding the mind and also trying to replicate the mind. So I got interested in like brain simulation, biophysical neuron simulation, and that's how I kind of that's what I focused on in college. And then gradually I shifted more from like the kind of biophysical neuroscience perspective to the deep learning, machine learning based perspective over time.
Nice, I see. And lately, it was like 1 month ago, I think, you wrote a great article on your blog called Just Ask For Generalization, outlining basically the recipe towards achieving generalization in machine learning with a focus in robotics. And basically the outline is first generalize and then infer compared to the direct optimization approach, meaning that instead of optimizing directly for a specific task, you train the model, your model on a very large data set with a broad distribution, and then during inference time, you condition on the task you want to solve. And can you give us a more thorough description on your idea behind this post?
Yeah, sure. So I can kind of give the high level description of like the intuition and the evidence of what we've seen in the field. And I can also, I didn't provide this in my original blog post, but I think there's a kind of more rigorous argument that one could make from the perspective of like, like a more principled reason for why this should work. But let me give the kind of high level intuition first.
Yes.
So circa 2014 to 2018, there's a very challenging problem in generative modeling and images where people were trying to get VAEs to produce non-blurry images. So if you recall, like when you train a VAE on some data set like CFAR 100 or face data set, you get pretty good diversity of images, and you might even be able to like control what latent factors spit out what image you want, which is desirable for a generative model. But the images are just kind of blurry. So like the edges of the faces would be a little bit like blurry, and you can obviously tell it's generated by a VAE and not like a real face. And then at that time, GANs are also a little bit ahead. So like they could generate sharper images, although, still often like not quite to the point where you could not distinguish it from a real image. But the GANs are a little bit better. And at the same time, though, they had this problem of like mode dropping. So you got less diversity than the VAE. At least that was the kind of folk wisdom of like the kind of trade-offs that you had between these two approaches. And there was a lot of like mathematical, discussion in academia of like why this is the case, or what is inherent about the VAE objective that might make blurry images. And people were coming up with all sorts of fancy losses, like or like normalization tricks and optimization tricks to try to solve this problem. And it was just like a lot of math. Like people were talking about like, you want really tight variational lower bounds, and they were writing a lot of code and theory to kind of justify some sort of low variance estimator for the true get that like lower bound on the lower variational bound on the likelihood very tight, because they thought that if you just get the log likelihood exactly right, then you won't have this blurriness problem. And then also, meanwhile, in GAN land, they were trying to come up with better F divergences so that the model would be kind of better mode coverage, right, and also get sharpness. And then like now, if you kind of jump forward to today, like in 2020 and 2021, there's these kind of language condition generative models like VQ VAE coupled with clip embeddings, where you can just do some prompt engineering on the VQ VAE, you append the string Unreal Engine to the end of your language prompt, and it will give you a sharp image, right? Like some prompts give you blurry images, but if you compose this VQ VAE string with like anything else that you want to generate, it just gives you a sharp image. And to me, that was like a big like kind of wake up moment that maybe we're thinking about like solving problems the wrong way, and maybe generalization and these kind of large models and the kind of space at which they can model different kinds of outputs. Because if you think about like blurry images versus non-blurry images, they're just two different modes of some very large distribution, right? Sometimes they're blurry, sometimes they're not blurry. So if there are two different modes of a very large data distribution, rather than optimizing for one mode, which is like the non-blurry images, and that's maybe pretty hard, what if we just learn everything and then just tell the model, give me the ones that are not blurry? And that's the kind of like design philosophy that I believe strongly in these days. Okay, so let me outline the general framework of how one would take this kind of way of thinking and apply it to new problems.
Yes.
So let's say you want to solve an optimization problem. You want to find the best set of parameters for some criteria. Normally, you would just optimize directly for it, or you just like kind of write some code down by construction that satisfies that property, and then optimize your neural net with that property as part of your model. That's also another approach you can do. Instead, what I'm proposing is gather a lot of data on problems that are related to that problem. So, for example, if your task is to let's say build a robot that can wash the dishes, very, very hard, long horizon RL problem. Instead, get the robot to learn all sorts of behaviors, like touch the dish, or like flop around on the ground like uselessly, or break an arm, or like at first, like the easiest things to learn are like the things that you don't want the robot to do, but you collect the data anyway. You also collect like whatever skills you can do, like maybe pick up the dish, or maybe like turn on the sink, right? Like so like you learn everything, and then you pair all this data with descriptors of what happens. So it doesn't have to be natural language. Let's just say for now, like you have some sort of way of specifying goal states, right? Like a lot of people in RL do goal conditioned reinforcement learning, where you show it like an image, or you show it like some kind of ground truth state, and it has to achieve that state. So at a high level, like you take your data set of like trajectories, and you pair that with descriptors, high level descriptors of like what they're doing. And importantly, these descriptors have to be like variables that humans can manipulate. So there's just like, let's just say for now we're going to use language to describe like what happened in all this data. Then you train this joint model, like let's say a density model P, the joint density over like your data, your robotics data, and your language data. So P of language comma robot data. And then so you, at no point are you collecting data for like wash the dishes, right? You're just collecting data, like all sorts of data of the robot doing many, many other things. And for many of these things, it'll be easier to collect than washing dishes, but maybe actually sometimes it'll do something that is pretty kind of, difficult. Like if you let the robot run for some time and it goes to several places in your house, you can relabel that as if that was the intentional, original goal in the first place. So this is this idea of hindsight experience replay.
Yeah, exactly.
Yeah. Just because the robot achieves something doesn't mean that it's not it could be relabeled as a really complex task. So when you collect this data set, it's easy to collect the data, but you can describe very difficult tasks after the fact, right, with hindsight experience labeling. So you have this broad distribution of tasks, and then the corresponding behavior that you need the robot to do the task. Then you train a joint density model on all this data. And then at test time, you infer the distribution P of robot data conditioned on the specific task that you want. And even though you're never directly optimizing for P of robot data conditioned on wash the dishes, if the model has seen enough language and seen enough robot data, it should be able to generalize by composing the language tokens together in the right way, and then also correspondingly the robot data in the right way. And then it'll give you the robot that washes dishes.
Yeah, and what I think is very interesting about this approach that maybe also differentiates from meta-reinforcement learning or meta-imitation learning is that you try to leverage the data with an efficient learning paradigm, for example, supervised learning, instead of reinforcement learning that is very, very simple and efficient. So is it correct, or how does it compare with the meta paradigm that we are seeing in reinforcement learning, etc.?
Yeah. So I'm not opposed to reinforcement learning, in principle. I'm suggesting supervised learning as a practical alternative for the following reason. Reinforcement learning algorithms seem to be very sample inefficient, and we have not really seen a practical application of reinforcement learning that can train on internet scale diversity, right? So I'm not aware of anyone who's trained an ImageNet classifier on ImageNet using PPO. Something imagine you have you formulate the image classification problem as an RL problem, and now you have to get the model to perceive things, right? People have built large scale image perception systems in our robotics lab and many other teams that work on reinforcement learning, but it's not any master's student or even undergraduate can download some code and train ImageNet in a few hours with modern compute, right? But the same cannot really be said from a practical perspective of training ImageNet with PPO. So there seems to be this kind of gap in terms of the ease of getting a certain amount of generalization, defined as let's say just perception on the internet size data set, compared to reinforcement learning. So if you want really rich behaviors, I feel the optimization capabilities of supervised learning are always going to be ahead of what reinforcement learning can do at any given stage of the period. So if what you care about is generalization, and if that's the thing that you really want to leverage, then just from a pragmatic perspective, I think betting on algorithms that have been shown to be able to handle this huge amount of data is what works. But that being said, if you have a more restricted domain where you know that reinforcement learning has already delivered something that can generalize, then that's also an appropriate choice as well. You just want to make sure that you're not crippling the optimization with unnecessary difficulty.
So do you expect in the near future to see some very large data set with maybe robots that perform many different tasks, and all these data are collected offline, and then there's some, as you said, supervised learning algorithm that learn from it and then is able to generalize to new tasks? Or still you will need some trial and error for, I don't know, as a form of fine-tuning for the task you want?
Yeah, I just realized I didn't answer your question about the meta learning. So just for the audience, I'll just describe what I think meta learning is, and
Yes.
meta imitation, meta reinforcement learning. So the motivation of meta learning and meta reinforcement learning is this observation that when we train our algorithms with both supervised learning and supervised learning and reinforcement learning, it takes a lot of samples, right? Like it's not something where you could just like plop it in a kitchen, it tries a couple times, then it gets it. It would have to try like hundreds of thousands of times before it gets it for like a vision model. And in the case of like state-based models, like tens of times, right? So that's not really ideal. Like, can you do better than that? And the kind of straightforward thing to do circa 2012 to 2015 was like just do transfer learning, right? You take a pre-trained model that can do a lot of stuff, you fine-tune it, and then maybe it confers some knowledge that helps speed up things. But there's no like guarantee that it'll work, right? So there's a famous paper called Taskology that studies like positive and negative transfer in a multitask setting, and they find that it's not that obvious to predict like what tasks transfer between each other. Sometimes you get positive transfer, sometimes you get negative transfer. So it's a little bit of an art of like choosing your base source domain that such that like when you fine tune it on your new tasks, it works. So motivated by this, and also with increasing compute, researchers are starting to ask like, okay, what if we just optimize our base model, our source domain model, such that if I were to fine tune it, it would do really well, right? So that you rewrite the problem into a sequential learning problem where first you train on some source data, and then afterwards you fine tune it, and then after the fine tuning, you measure the performance of the task that you want to fine tune on. So there's many ways to write this algorithm. You can do like gradient-based meta learners like MAML, which kind of rewrites the objective as like, what is the performance of my system after I take a gradient step, and then you differentiate through the whole thing. You can also rewrite this as an RNN. So like, the first part of the RNN ingests the data, and then it spits out something that can conceivably approximate the fast update behavior in order to satisfy the loss on the second stage. And so my understanding of meta learning algorithms is like, you formulate a sequential problem in which you have to update quickly, and then you optimize for updating quickly. So now your question, going back to your question, is like, do we still need this, right? Meta learning, similarly to reinforcement learning, so meta learning can do some pretty cool generalization capabilities, right? It can do few-shot learning, and it often achieves state-of-the-art few-shot learning on benchmarks like CFAR10, like tiny ImageNet, things like that. But meta learners have not successfully been deployed at doing like few-shot learning on ImageNet size data sets. So going back to my earlier point about like reinforcement learning lagging supervised learning, meta learning is better than supervised learning in some ways, but it also lags in other ways, which is that the scale of problem that you can attack with a meta learning system is lagging behind supervised learning. And it's not because the algorithm is flawed, it's just because it takes more compute to do the meta learning thing. So for any given level of compute you have to do a supervised learning problem, you have to take a pretty big cut to apply that same idea to meta learning. So if you want to push for generalization, yeah, meta learning can get you that in some dimensions, but it also makes you lose some like data absorption capacity in other respects. So with the question of like whether you need meta learning for robots, I wonder if there's a way to get more computationally efficient meta learning. One of the results that was very encouraging to me was the GPT-3 paper, which showed that you can get meta learning behavior out of any sequential model that's like trained on sufficiently large data, right? Like they train it on next word prediction, but by prompting it on stuff, it can also do few-shot and zero-shot learning. So if that's true, then maybe you don't actually need the computational overhead of explicit meta learners. Maybe you can just train a sequential model on a sufficiently large data set. And if the data set is rich enough, the meta learning or the few-shot capability will just emerge naturally out of the sequential inference capabilities of the model.
Still, GPT-3 requires an incredible amount of computation. So I wonder if this strategy can still work with sequential tasks that the optimization is much more difficult and longer. So you need both the data set that I think nowadays it's almost impossible to find, but also really a lot of compute, though maybe generally less than meta reinforcement learning or whatever.
Yeah. So yeah, I think that's very possible. And to be frank, I'm not an expert in like the sample efficiency of large scale models or language for that matter. Yeah, that is a concern. And when I first saw the like cost of training GPT-3, I think it's somewhere quoted around 10 to 12 million in public cloud costs.
Yeah,
that was very depressing to me because, you know, even if you believe in like Moore's law, right? Like, and I actually kind of do believe in Moore's law. Like people say it's slowing down, but I actually think it'll go longer than people expect. So, but even if you expect that cost halves every 18 months, it'll be quite some decades before it's kind of practical for a regular person to train a GPT-3 level model from scratch. And never mind like doing science, right? Like science often requires running many variations of like the same model. And so just like the science of these models has become intractable for like academia. And that was very depressing to me because like I have my own GPU box at home and I want to like, you know, try certain things. And if all the capabilities are just beyond reach for regular programmers, then that's kind of a sad place to be. Something that has been kind of encouraging is that like, I think we shouldn't underestimate human innovation. And in the last 12 months, a lot of people motivated by this have kind of cut down the cost of training a GPT-3 level model. So did you see DeepMind's recent paper, Retro?
No, I didn't. What is it
about?
So,
okay, so here's the link. Okay, so one of the problems with GPT-3 is that it requires the entire neural network to memorize this very large corpus of text, right? Like, even though it's supposed to like compose things together, but like all the knowledge and all of the computational ability is kind of put together in the same place. And this can be very parameter inefficient because it requires a lot of parameters to store like the raw text in some ways so that you can then retrieve them, right? So what the folks at DeepMind did recently in this paper that they released last week was they have this external lookup table that the model can query tokens from. And it saves a lot of capacity and it saves a lot of compute as well. So
from a vocabulary point of view, or just store some weights of the transformer?
It saves compute from, I think, the training perspective because you no longer need to train such a big model. You split the knowledge and the kind of computational and thinking ability of the model into two separate pieces. And I'm not suggesting that this is the way of the future. I just bring this up as an example of like a way to drastically reduce the assumptions of how much compute you need to scale. And similarly, I think other works at Google and Facebook have like built variations that have more sparsity or have some sort of masking scheme that lets you have less compute. And I think these will also give us a sort of Moore's law effect where like you can think about Moore's law of transistors speeding things up and making things cheaper, but there's also kind of like a Moore's law of AI researchers where every 18 months or something, AI researchers will make the same performance achievable with less compute or less money or some access like that.
It's like probably like with ImageNet at first, it required a really big amount of compute, but then with innovation in hardware and more efficient algorithms, now you can train or basically any GPU. So
yeah. And I think I give great credit to like OpenAI for like putting GPT-3 in like the popular media, because without this kind of like hype cycle, you wouldn't get so many technologists and academics and students interested in trying to kind of make it more accessible to everyone, right? Like the fact that people see the promise of this has poured a lot of money and investment towards making this technology more accessible. So in a kind of weird, like ironic way, like there's people who criticize like the kind of waste and scale of these large language models, but this is kind of like weird path that happens through history where like enough interest in something can actually make it less problematic in an energy or climate kind of way.
Yeah. Transitioning a little bit from your blog post to more the stuff you're doing on the research side. I saw that you put a lot of paper where you design algorithms that combine both data from demonstration and trial and error. So you fuse both imitation learning and reinforcement learning. Can you first explain the advantages of learning from both demonstration and trial and error?
Sure, yeah. I can give you kind of like a textbook answer of why this is like, desirable. And often when people motivate their talks, they'll say these kind of things. And then maybe like, I'll also suggest like some more non-obvious ways in which that's useful. So the first one is just like a kind of intuition that, this is what animals and humans should do, right? Like when we learn, we are using our failures to kind of get better. So intuitively, if our algorithms are only relying on successes, then something is wrong here. And also, like conversely, human babies demonstrate a lot of imitation capability. And if your algorithm is just trying to solve some sort of problem from scratch, it also seems a little bit inefficient because that's not really how animals and humans learn either. So there's this kind of like naturalistic fallacy that we often look to when we're motivated by algorithms that can learn from both data. Another answer is that like it's time and time again, people have shown that it's possible to develop some algorithm that uses data from both failures and successes or demonstrations, and you get better than the best of both. You do better than like either of the parts alone. And I think it's possible to kind of construct these settings in a contrived scenario where if you have some optimal trajectory, and then you have some failure data where you deviated from the optimal trajectory, then you can use at least that failure data to make your optimal trajectory more robust because you know what not to do. And vice versa, if you were on some suboptimal trajectory and then suddenly you did better, you can maybe combine parts of an optimal trajectory with a suboptimal one to do the best you can given your data. So intuitively, from an algorithmic sense, it makes sense that like regardless of whether your data is pure demonstration or trial and error, they have kind of complementary information in there, and if you use both, you should be able to do no worse than I did. So that's the main motivation. And I wouldn't say that I've published extensively in like this kind of like imitation and RL stuff. A recent work that I was on was called AWOP, led by my colleague Yao Lu. And in that paper, we were basically just trying to take like off-the-shelf modern offline reinforcement learning algorithms that conceptually allow us to combine reinforcement learning and imitation together. And we were finding that they weren't working. They work on smaller problems, but at scale, like on real robot data, things kind of go wrong and it's not very stable. And in fact, actually, working on this was sort of the one of the kind of experiences in my career that led me to write the Just Ask For Generalization, because I was seeing how tricky it is to kind of just like optimize an RL objective properly. So we were finding that a lot of the stuff wasn't working, and then we were just tweaking the algorithms until it worked, and then we called that AWOP.
And so do you think that for performing a general task for a robot, so we are not speaking about general purpose robot, it's just a more simpler one. Do you think it's better to use such approach as in AWOPT, or still you need to use a more general paradigm, such the one you outlined in your blog post?
Okay. What kind of task do you have in mind here?
Very simple one, just like, I don't know,
pick and place or something?
Yes, or hand manipulation, these kind of things. So maybe
so some sort of like atomic task that you can do within 10 seconds, something like that.
Something like that.
Okay.
Yes.
Okay. So yeah, so I earlier I said like conceptually there's advantages to like combining imitation and reinforcement learning data, and academia shows this. when you want to scale this up to a real robot system, there's a lot of like intricacies that come into play here that require like very careful engineering, and in some ways like solving other research problems before you can even use your desired like RL imitation, like ILRL algorithm. For instance, like when you just train an offline reinforcement learning algorithm, it's not really easy to know whether it'll just work, right? Like often you just need to evaluate on the robot, or maybe if you have a simulation, you could try it in simulation first. It so happens that if like just because something is working in simulation with an ILRL algorithm doesn't really give you that much indication of whether it will work in real, because RL algorithms can maybe exploit the simulator, or maybe there's something about your sim data that isn't as complex as your real data, and so when you train it on the real data set, maybe like bad labels or something in your real data can throw off your algorithm, or even just like the percentage of like relative successes and failures you have in your starting data set can have a huge impact on whether your algorithm converges or not, right? So what I'm saying here is that like the transfer from like a sim experiment to a real experiment often is not that straightforward, and it requires intermediate steps to de-risk that. So one of the important intermediate problems is just to make sure your sim and real are really, really aligned. Like you want your sim to be as close to real as possible, because then if you have a pretty complex algorithm that's very hard to debug in real, you want to make sure you do all the debugging in sim, and then when you just put onto real, because your sim and real are very similar, it should just work, right? That's kind of like the way that we believe of how to debug ILRL algorithms. But then that means that you have to solve this intermediate sim to real problem, which is like getting your sim to be as close to real as possible. And like, what does that mean? And what does it take to do that?
There are many techniques for the sim to real, or you also can use domain randomization on the simulator. But do you think that the simulator can be used both for training and evaluation? And how much of your real world data do you think should be used for learning a robotic task? Can you do everything in a simulator, or you still need some real data?
Yeah, I used to be very like skeptical of simulation because, you know, again, naturalistic fallacy, right? You look at humans and animals, and like a giraffe can walk within like 30 minutes of being born. So, and it clearly doesn't have access to Majoko or anything like that. So like maybe there should be some way to learn very quickly in real. But, you know, as like kind of an engineer in the last few years, like I've kind of realized how painful it is to try to do experiments on general purpose robots. So not for the sake of like finding an ideal learning algorithm, but for the sake of just like, you know, moving fast enough to not be frustrated and being able to eval many ideas as opposed to like one idea per day. I strongly believe in simulation now. That's like, I think that's the way you scale up robotics is, and you know, the progress of the field is like in robots has been pretty slow for the last decades compared to software. So I think the more we can make robots like iteration done in software, the better. So while I don't like simulation from like a naturalistic fallacy perspective, I think it's indispensable if you want to try anything harder than behavior cloning. So if you want an ILRL algorithm, you need a simulator. If you want something that's like, you know, has external memory or has some sort of fancy kind of like learning trick embedded in there, such as meta learning, you need a simulator, because it's not going to work like if you just implement it once on the real robot. And as for training versus evaluation, I think training data, yeah, that'd be nice if you could use training data, but that kind of has an even higher bar in terms of like how good the simulator has to be.
Okay, so now you're saying using the simulator just for evaluation.
I think that's my first priority. Often people talk about simulator as like the, you know, for training data, but and in fact, I actually think that gathering data is not too hard. The problem is like, it's like if you're not throwing your data away, you can accumulate a lot of data quickly. So gathering enough real data to learn a good policy is not difficult. What's difficult is like trying to know what works, and if your system has to generalize to like 10,000 different things, it's not really feasible to like evaluate that experiment in the real world anymore. So you need some way to do careful science without paying that cost. And I think that's where simulation is like indispensable. I think if you can't train on simulation data for your robot, that's okay. Although like it would be certainly really nice if that was factor as well, because then you don't have to gather that much real data. And in some ways, like if you have a recipe that can use your sim data to train a good real robot, then you can, then you're off to the races, right? You can just do everything in simulation and it'll just work.
You are a big proponent in end-to-end robotics. So do you think that ultimately every robot will be trained end-to-end? So perception, prediction, and control, or for some tasks on other particular cases, it's better to have two separate parts, perception and prediction and control?
Yeah, that's kind of like one of the big questions and hot topics for debate, I guess, in the machine learning field overall, right? Like, how much structure do you want your systems? Is end-to-end going too far? I think people who like disagree with the end-to-end kind of perspective have been sort of how to say, like, saying this for the last 10 years, right? Like, even as the end-to-end kind of keeps on growing in scope. So I think robotics is also such a hard problem that it's like we need to disentangle where we are today versus where we want to go. And like when we talk about whether end-to-end makes sense, whether we're talking about like systems we have today or the systems we want in the future. So for systems that we have today, like let's say an industrial pick and place system, they have such high reliability requirements that an end-to-end approach probably would not do well on it. So for example, many pick and place startups like Covariant or many of the other competitors as well, and Amazon has their own internal one, they are all more or less like pretty well-tuned object pose prediction and classification detection systems, right? So it's just a perception network that does pose estimation, and some startups don't even do the pose estimation part. They just maybe use like instrumented LiDAR sensor or something instead. And those are kind of more mediated perception, and then you pass the perceived scene graph into an RRT planner, and then your open loop planner or closed loop planner will just execute the strategy. And this is nice because you know what the system is supposed to do, and if something is not working, there's a very clearly well-defined like recipe to de-risking that, right? Like whereas with end-to-end robotics, it's very risky from a technical perspective because we don't have any kind of grasp on what it takes to generalize for a certain problem. So I'm working on a follow-up blog post arguing like what are the properties of generalization we want, and it's tricky, right? Like the central question is, given my problem, how much data do I need to gather, and what kind of model do I need to generalize to a given test case that I haven't seen before? That's incredibly hard to answer. We don't we have theory that can tell us basic definitions, but we don't have theory that can answer like how many different types of objects do I need to collect data on in my pick and place system to generalize to any object, right? Like that's just sort of unknown, and it's just researchers' intuition. So I think like in the short term, the end-to-end approach has severe limitations that like have very valid criticisms against, if you want to build a system that works. But if we looked at like the long-term, aspects of robotics, like where do we really want to go? I think the end-to-end approach is the only approach that could work. And I'm not saying it will work. I'm saying that it's the only one that could work. And if it doesn't work, then we're screwed. So consider like a robot that can operate in an unstructured kitchen, right? Like, and you want to build something that can, I don't know, just spread some jam on bread, right? And I have like a blog post that kind of articulates, how seemingly how such a seemingly simple task of like that, you might like put on some sort of basic analogy of like programming actually becomes really, really complex if you want to do it in the real world. Like, what if there's no more bread in the bread box, or like what if it's just the crust and the human doesn't like the crust, and what if like what if your finger can't hold the piece of bread correctly for some reason, or if your jam falls off the knife. Like the reality is just like it's very full of detail and edge cases, and it's chaotic, and I don't think we have the ability to distill the semantics of the world into a formal logic that can be executed on a robot. And when you think about like compositional systems, like non-end-to-end systems, what we're really saying is that like we're defining a formal logic, like a contract between a stage of a pipeline that does something and then the next stage of a pipeline that does something else, right? So the formal contract between perception and control is like, I hand you a scene graph, and then you plan with respect to the scene graph. And then the formal logic also just like makes the assumption that like, you know, the state of the world that you're perceiving is more or less correct, and you might even pass uncertainty or something, but it's more or less correct, and then it's just a matter of planning. But what if like something in the world happens that breaks that assumption? Like what if you need to actually go back from planning back to perception again? Or what if like perception actually requires memory because you've occluded something that you can't see anymore, and you actually need some sort of recurrent perception, right? So the world is so complicated, and I do not believe that if we want general robots, it's possible to decompose reality into formal logics and ontologies between perception and control.
Maybe you can also fuse both approaches, meaning that you can build some logic from the perception part and the ontologies, how you said, but still leave a latent space that is trained end-to-end, so that the planning stack is able to use both inputs, the one learned end-to-end, so that maybe it's still able to learn something that you cannot have anticipated before. But also you can inject some prior knowledge into the system so that you can, for example, bootstrap the perception part or something like that.
Yeah, I think if you kind of like talk to people and like, and debate about like end-to-end versus hand-coded scripted logic versus like mediated perception, I think actually everyone sort of agrees more than they disagree, which is like you want more learning at the end of the day, and eventually you want a system that kind of can tune everything, so that's practically end-to-end. But then people might just disagree on like how you get there, right? Like, so some people believe in building something that has planning by construction. So for example, you build a really good world model, and then you use an RRT planner off the shelf. Whereas maybe someone else, for example, like myself, might not believe so strongly in planning and say like, okay, you want planning, but you want to implement it more as like an amortized search. So something more like what AlphaGo does, right? Where you use the planning to give you data, and then you just distill the data into like amortized inference. And that's just a matter of taste, right? At the end of the day, it's still like the same inductive bias. It's just like where you choose to use it. Like, do you want that inductive bias like at test time, or only at training time, or data collection time? And it's just kind of variations on implementation details.
Yeah, I also wonder if in the long run the end-to-end approach will win, and we use the perception stack that has been trained from an agent that is able to interact with the world, also for the task that involves just perception. For example, I don't know, object detection or semantic segmentation. Maybe also this will come from a backbone trained, for example, end-to-end, because the agent that interacts with the world is able to learn better what means to be an object, or it has more knowledge about physics, so it's able to create a better perception stack.
Yeah, that's a great question. So, going back to what I was saying earlier about like supervised learning always having sort of a lead time ahead of like RL in terms of generalization capability, I strongly believe this is true for robots. So for example, like, we're training robots with like pretty large data sets these days, but it's, if you kind of like qualitatively think about the richness of these data sets, it's still not as rich as like what we see in perception. And so if the goal is to build general purpose systems, I think that people who are working on the most general data sets do have some sort of lead or edge in terms of like the kind of capability of the system in some axis over what people in robots are doing, right? So I sometimes envy like how quickly people in vision and natural language domains can like publish papers, because they just like, run 30 experiments at a time, and like they don't have any problems with evaluation, and all this code is already set up, so they just need to tweak like architectures, right? Like that's really cool. And I think robotics needs to go there. I have this mild like fear that robots is not going to be solved by some roboticist or some reinforcement learning person even, but like some person who works on like visual question answering. Like I could really see this kind of outcome in the future where like the world expert in visual question answering is a better roboticist in some ways than like the world expert in deep reinforcement learning. Because the visual question answering person knows how to tackle generalization in the kind of broad open structures scope better than the roboticist can. And that person will also think about the more kind of like general approaches. And then once you have that kind of backbone, as you mentioned, something that understands language and questions and images, it's just like a few like steps away from building something that can perform control as well, because something that understands enough about vision and language presumably has the right underlying structures to also reason about control.
What's your opinion about self-supervised learning? Do you think that it will play an important role in robotics, or maybe in 5 years will not be useful anymore because we found a more efficient way to train the different parts of robotic stack?
Just for the audience, self-supervised learning is this kind of term that has emerged with great popularity in the last few years. I think also used to be branded as unsupervised learning, but I don't see a big distinction between the two. But the basic like idea of these kind of algorithms is that they take your observation data, your data that's not like created by human labels, and then you generate like auxiliary prediction tasks. For example, in a contrastive approach, you take two invariant things and you push them together and you push them away from something else in your batch. But there's other things like BERT, which are like masking and even like density modeling can be considered as sort of an unsupervised algorithm. And there's implementation details on whether you use contrastive or fully observed likelihoods. But at the end of the day, they look a lot like some sort of dense, implicit or explicit density modeling on your data. I think that they're really great. And I think that self-supervised learning algorithms look a lot like supervised learning algorithms, except that they're using different labels, right? Essentially, you're just taking your data set and you're formulating a new supervised learning problem where your label is very cheap to compute.
Yeah, it's labeled that is intrinsic in the data. It's not being labeled by some human.
Yeah. But then the distinction between self-supervised and supervised is just a matter of cost, right? Like if the distinction is just like how much money does it cost to get you that label versus a human label, then there's no, like from an algorithmic perspective, there's nothing really like different about the self-supervised label from the supervised one. It's just it gives you labels for a different problem. And then the question is like, does that other problem give you transfer enough knowledge to your supervised problem or the problem you actually care about? And I think the answer so far and demonstrated in literature is that it's usually yes. Like it's possible to get some extra juice out of your data set by formulating these auxiliary prediction problems in the form of like, contrastive learning or something. So yeah, broadly, I think that these things can give you more data. But let's consider like an alternate counterfactual of like what situation might happen that this is no longer that helpful. Maybe if we get to the kind of scale where you have so much data that it's like infinite and you're bottlenecked, like given a certain number of flops of compute, you can choose to spend them on computing, like training on supervised labels or unsupervised labels. I think in that regime, maybe self-supervised learning doesn't help as much because you would prefer to spend the compute training on your infinite supervised labels, right?
It's like the case in GPT-3 or Clip, where I don't think that they use any pre-training or self-supervised task, because you already have a huge data set, so it doesn't make sense anymore to use pre-train on some other task that may not align with the final one.
Yeah, and these, from a scientific perspective, these kind of experiments are very difficult to conduct. So let's say you have some idea, like some sort of self-supervised idea that can further improve CLIP or something, and then you implement it, and you find that the performance curve goes faster than what the original CLIP paper does, right? Like you show some sort of, my idea can give you faster convergence, and therefore it's better. But if you don't control carefully for like the number of flops, of compute, then it might be the case that like you're spending double the flops of the original clip objective. But then that means that like if clip just spent 2x the amount of flops, they could also maybe get a similar benefit as well. So like when considering like the infinite labels regime and whether you have some sort of self-supervised idea, you have to make sure that you're like accounting for the baseline where the baseline method is given that many more flops and therefore that many more like passes over the labels on the data. And so maybe in that regime it doesn't help, but I could also see a very likely possibility where it does help, because maybe the training on an auxiliary problem actually confers some sort of robustness that the distribution of labels themselves don't give you. Although it probably depends on the problem.
Yeah, yeah. And I have a final question. What's, from your point of view, the major obstacle for achieving a more general purpose robot? Is it about acquisition of data, or is it for the computes that we don't have enough, or what's your point of view?
Yeah, that's a great question. I'm glad you asked it. So in the last year, I've become much more interested in like organizational and people problems and culture problems than I am about like the technical challenges. So I think the biggest obstacle to moving robotics forward is actually not something like, you know, computer data or benchmarks or anything like that. It's the challenges of getting people to work together on this really, really hard problem. And I think there's a lot of problematic incentives in industry and academia and just like long-term thinking in general. So let's consider like, you know, okay, so robotics has been around for what, 70 years now? I think ever since like 1950, people were building like mechatronics, right? It's been around for many decades, and everyone kind of has this idea of where we want to go, which is robots that are helping us around the home. But like, where are the robots, right? Like, why don't we have that yet? And I think it's because of people. I think it's that like there's, you know, people are building really great things, but they're not like putting things together fast enough. So let's take one example. Like in Japan, they are the world's experts at building humanoid robots. They're very, very excellent hardware and systems. And it's not like, and you know, many researchers, robotics researchers believe that like the humanoid morphology is kind of what you need to accomplish the full scope of tasks. Of course, there's like problems with control, right? So like no one really knows how to safely and reliably learn on a humanoid scale system. But like everyone kind of knows that like a humanoid would be really ideal, and maybe even some people dare to like propose algorithms that they think could work on a humanoid. So like, why isn't anyone doing deep reinforcement learning on humanoids these days? Well, one is that like the people who build humanoids don't make them very accessible for other people to do research on, because maybe they want to do it in-house, or maybe they have like some sort of like a concern over IP. So with respect to like industry humanoids, they want to make money on them. So their priority is not like making them as widely accessible as possible. And then with academic humanoids, like in the ones you see in Japan, it turns out they're not actually that interested in doing learning on them. They're more interested in writing papers about like how do you make the robot better at passive cooling or something, which is an important problem. But like, you know, there's this kind of, I think, tragedy of the commons where like everyone wants to either like make money with their proprietary system or publish a lot of papers and not let other people like scoop them and stuff. And so as a result, we're not getting enough like kind of cross collaboration the way that you see in like image and vision communities. Like so for example, in other communities, like things are so easy to re-implement on code that like you just publish the paper and someone else can instantly like, you know, reproduce it and scale up and take your ideas, right? Whereas in robotics, there's this kind of hardware element to it and a huge software component to it that we don't have as much like sharing between or building on top of each other's work. So even though the vision is clear, I don't even know how many decades it'll take before like we can, let's say, have like a Tesla equivalent of like humanoids walking around, right? And it's not that the technology isn't there. The technology is already like there and de-risked in its components, but no one is daring to just like put it all together.
And do you think that single company like Google or Tesla should be able to do that, or you're talking about a more cooperative world level research that put everything together, but it's a very great team.
Yeah, I don't know like whether industry or academia is the best way to do either of these things, because I think both of them have like their respective drawbacks. I do admire Tesla a lot. Like, you know, they have this new like Tesla bot thing that they're working on, which is a humanoid, and presumably they're going to use like similar infrastructure for the self-driving cars on that. So I greatly admire like that kind of ambition. But like, it's such an obvious like, it's kind of like weird to me that like we treat that as kind of like an anomaly, right? Like why isn't that the norm? Like, why hasn't every company that calls itself a robotics company tried to like build something like this? And so with Google specifically, I don't think I can comment too much because, you know, for privacy reasons, but that is something that we want to do as well, like general purpose robots. But there can be like many kind of small like bottlenecks in the way, such as like academic incentives, or maybe like, you know, we don't have humanoids, for instance. So like, what if, you know, we're just going to do all our research on non-humanoids, and maybe that's also a big bottleneck as well, right? Like there's just some tasks you can't do with non-humanoids. And you know, there's still plenty of work to do in like with non-humanoids. I'm just saying like the long-term vision, like if the goal is to get them as soon as possible, it's kind of odd to me that we haven't taken all the pieces that we know already are there and just put them together.
In the case of Tesla, because they have already a full deep learning stack, do you think that is clonable, the code in the Tesla bot from the cars, or they have to rewrite most of it because, I don't know, the robots need to control every part in a different, much finer way, or it perceive very different environments and so on?
Yeah, that's an interesting question. You're asking kind of like the hard question, which is like, how much generalization can you expect, right? Like, if I train on the universe of like self-driving car data, presumably it has some interesting information like how do people behave, how do you read signs, how do you like understand objects in the world, right? But maybe it doesn't have knowledge about what it means to hold an object in your hand, or what it means to collide with an object, because like they presumably don't want to like the car probably doesn't have any training data in the regime where it's already crashed with something, right? So whereas like if you're trying to manipulate objects, you have to collide with them. So I'm just speculating. I don't know what's in their data set, but like I think there's probably going to be some things that are definitely not in their data set, no matter how smart an AI is trained on self-driving car data. But there might be plenty. Like maybe a self-driving car data set like that's paired with language, like maybe that actually understands enough about the world that it doesn't take too much additional language to like reason about what would it be like to be inside a home, which a car has never seen. But like, you know, it's a stretch, right? But it's possible, I think.
But if it's just a data problem, that you can do some kind of transfer learning domain adaptation to the new distribution. But also it's remained to be seen if the stack they have is transferable to different.
And I think also there's like organizational challenges as well, right? Like let's say tomorrow, you know, some big crisis happens with the car stuff, and like that causes the Tesla bot to be deprioritized or something. Like, you know, companies are often like beholden to their shareholders in somewhat short-term thinking ways, and I think that can also be a challenge for like long-term thinking, right? Like if you want to build rockets that go to Mars or build robots that can help people in homes, I think just like the world we live in doesn't really kind of incentivize that sort of long-term effort. Even like people's careers. Like I know people like they don't care so much about like the solving the long-term aspects of robotics. Like life just kind of changes your priorities in ways, like, you know, and that can also remove talent from the talent pool, right? So I think another issue with the people problems is like keeping people who are committed and focused enough on these kind of long-term problems so that they continue caring about it, even as like things in their life change or their priorities in life change as well.
Yeah,
that's another challenge as well.
Yeah.
Like people get into middle management and they stop caring about robots and they care more about like management, right?
Yeah. Yeah, sure. Okay, thank you. I'll post everything in the comment section below so that people can reach you and read about your blog posts. And do you want to share something else?
No, this has been really great. Thanks for letting me,
Okay.
share all my opinions, and I really appreciate it.
Okay, so thank you very much, and it's been a pleasure to have you here, and see you on the next time.
Yeah, let me know if you're ever going to a robotics conference or something, or in the Bay
Sure.
Area.
Okay, thank you very much.
Take care.
Bye, Eric. Bye-bye.